All right, good morning, everybody. So quick announcements before we start this lecture. No in-class assignment this Friday, so that means regular lecture. And there is a homework to on Thursday, chapter 2, part 2. Okay, so don't wait for the last minute. We'll make hard on you. Okay, very good. So let's pick up where we left on Wednesday. So I think that was the last thing I showed you guys. So we are talking about molecular mass. So remember that molecular mass will take into account all the atoms that are present in the structure of the molecule. And you can always use that 1 mole of molecules contains 6.02 times 10 to the 23rd molecules. For the example here, we have a sample that has 2.5 grams of calcium fluoride. And if I'm not wrong, we tackled A and B, and what's left here is C and D. And I will go over, and we will move on to the next topic. Okay, so everything starts with the formula of the compound. So you have to have the concept clear in your mind, how to, from the name, get the structure of the compound. Calcium fluoride, calcium 2 plus, chlorine 1 minus, draws the charges. Therefore, the formula for the compound is CHEM. Okay? Once you know the formula, then the determination of the molecular mass is very simple. So we are going to add up all the elements that are contributing to the formula. So we have here 1 atom of calcium and 2 atoms of chlorine. So to speed up the process, we will have here a molecular mass of 74.0 grams per mole. Be careful here. The problem asks for 3 sig-figs, so that's why I stopped with 1 decimal spot. Okay, so the molecular mass means that in 74 grams of calcium fluoride, we have 1 mole of calcium fluoride. Okay, so therefore that's the correlation. So let's tackle item C. How many moles of calcium fluoride are in 2.5 grams? All right. So 1 mole of calcium fluoride we can always replace mole by 6.02 times 10 to the 23rd molecules of calcium fluoride. Okay. And from the molecular mass, I know that 1 mole of calcium fluoride has 74 grams. Okay, and that's going to be our third part here in the conversion method. Yes.
I got a different answer for B. I got 78.1.
Let me see if I messed up here. Oh no. See, fluorine. Right now. 78.01. Sorry about that. Okay. All right, thank you. Okay, very good. Okay, so once you know the conversion factor, you can use two parts of the conversion factor, whatever you want, depending on what the problem is asking. So here the information given is the mass, and what we want to know is the number of moles. Okay? So therefore, the last part and the first part of the conversion factor will have the information that we need to solve the problem. And here we always end up in a proportion. So the first column, I'm going to write everything that relates to mole. From the conversion factor, 1 mole is equivalent to 78 grams. And therefore, the second column here is grams. In 2.5 grams, so let's divide everything now. Now in 2.5 grams, how many moles do we have? Okay. Simple proportion, cross multiplication will solve the problem. We'll speed up the process here. 0.03. Okay. Okay, so therefore 2.5 grams of calcium fluoride are equivalent to 0.03 mole. Okay, so now be very careful with the last item of the problem. Okay? How many atoms of fluorine are in a sample containing 2.5 grams of calcium fluoride? Okay, so let's look at calcium fluoride. So very simplistic representation here. We have 1 calcium and 2 fluoride ions in the form. Okay? So this whole thing is 1 molecule of calcium fluoride. Always pay attention here to the coefficient. So therefore, if I take 1 mole of calcium fluoride, for 1 mole of calcium fluoride, we will have 2 moles of fluorine, okay? So each mole of calcium fluoride has 2 moles of fluorine. And this number came from the formula. We can always replace mole by 6.02 times 10 to the 23rd atoms of fluorine. Okay, so now we have a relationship between moles of calcium fluoride and atoms of fluorine. So we will build the proportion again. On the left side, moles of calcium fluoride. and on the right side, atoms of fluorine. For each mole of the compound, we have 2 times 6.02 times 10 to the 23rd atoms of fluorine. In 0.03 mole, how many atoms do we have? Okay, so always pay attention to the formula, the coefficients for each element, and what the question is asking you. Cross multiplication will solve the problem here. Let's see. 0.03 times 2. Okay, and we will end up with 0.36 times 10 to the 23rd atoms. Okay, you can always move the decimal point to make 3.6 times 10 to the 22nd. All right. So stoichiometry is a subject that requires a lot of training. So we will do some exercise in the discussion today and also in the homework. All right, very good. So let's go back a little bit and talk in depth about chemical equations. So a chemical reaction is a rearrangement of atoms. Atoms cannot be created or destroyed. So therefore, in any chemical reaction, the number of atoms for an element before has to be the same after the reaction. We cannot lose or gain atoms on the way. Remember here, everything before the arrow are reagents or reactants, and everything after the arrow products. The numbers in red are called stoichiometric coefficients, and in blue is the physical state of each component. The stoichiometric coefficients in the chemical reaction will tell us the proportion between the reagents and how much product is formed. Thus, knowing a chemical reaction for a given process allows one to predict the amount of product or products formed or reagents needed. Therefore, the chemical reaction will tell us the exact proportion for each reagent and how much will be produced. Therefore, if we read A plus 2B producing AB2, what the reaction is telling us is that 1 mole of A reacts with 2 mole of B producing 1 mole of AB. So the ratio in mole, attention, the ratio in mole comes from the stoichiometric coefficient. And those are the numbers that I wrote. 1 for A, 2 for B, producing 1 of AB. Okay, so that's the first information that the reaction will give us. However, before doing any stoichiometry, so we're going to pay attention regarding the balancing of chemical reactions. So balancing means that the number of atoms for each element before is the same after the reaction. So remember that a chemical reaction is a rearrangement of atoms. And atoms cannot be created or destroyed. So let's take a look at a very simple reaction. Hydrogen reacting with oxygen forming water. If we don't balance this reaction, we have here 2 atoms of hydrogen reacting with 2 atoms of oxygen, producing 1 molecule of water. So at the end, we have the 2 atoms of hydrogen, however, just 1 atom of oxygen. So this reaction is unbalanced because the number of atoms for the element oxygen before is different after the reaction. Okay. So we started here with 2, and at the end, there is just 1. So what we are going to do to balance the reaction is to introduce stoichiometric coefficients to ensure the same number of atoms before and after. So let's write the equation. Okay, so attention here. those numbers cannot be changed. So we are not going to mess up with them, but we can multiply each reagent or each product in order to achieve the balance. So if we look here, there are 2 atoms of oxygen before and just 1 after. Therefore, to balance the oxygens, we are going to add a number 2 in front of water. Okay? So now this number 2 will multiply the number of atoms for each element. So now we have 2 oxygens. Okay? So therefore, this is balanced. And 2 times 2 for hydrogens. Yes.
You should probably put a 2 in front of the H2 for that reason.
What?
You should probably put a 2 in front of the H2.
That's my next step.
Okay.
Yes, exactly. Okay, so balancing the oxygen created an unbalance for the hydrogen, because now we have 4 and just 2 before. So then we need to balance here. So now 2 times 2 for atoms of hydrogen. Okay? So therefore, hydrogen is also balanced. And if you want, you can put a number 1 in front of the oxygen. So this way, now all the elements are balanced and the reaction is balanced. Reading the reaction, 2 moles of hydrogen reacts with 1 mole of oxygen, producing 2 moles of water. So that's the story that the chemical reaction will tell us and give us all the proportions that we need to. Okay, so at this stage, balancing reactions is a trial and error method. You attribute coefficients and check. If they are matching, good. If not, you try other numbers. Okay, so after balancing the reaction, what we are going to see is something like this. So now we have 2 moles of hydrogen, so 4 atoms of hydrogen before, and 4 atoms of hydrogen after, balanced for hydrogen, 2 atoms of oxygen before, and 2. Therefore, reaction is balanced. Okay, so let's think about this problem here, and then I will give you a couple minutes and go over A and B, and then C and D you can do it. Okay, so let's start with the first one here. So when we have more complex chemical reactions, what I like to do to start with is to look at the element that's present in only one reagent and only one product. So if you look here, I only have sodium in one of the reagents and only in one of the products. So that sometimes is easier to start with. And same thing for boron. Okay? So therefore, the only place that I can have to balance sodium and boron are here and here. Okay? So now let's see if they are out of balance or they are already balanced. One atom of sodium before, one atom after. Same thing for boron. One before, one after. So that looks good. So let's leave one and one for now. And we can always go back and revisit it. Okay, so now let's take a look at oxygen. So only here and here. Before the reaction, there is just one atom of oxygen, and after, 1 times 2, 2 atoms of oxygen. Unbalanced, so we need to balance the number of atoms of oxygen. So let's add a coefficient 2. So this number 2 will multiply the indexes So now we have 2 times 1, 2 atoms of oxygen before, 2 after, so that's balanced. And what's left is the atoms of hydrogen. Attention here, we have hydrogen in the first and second reagents. 1 times 4, that's 4 atoms of hydrogen in the first reagent. 2 times 2, 4 more in the second. So therefore, we have a total of 8 atoms of hydrogen before and only 2 after. So therefore, to match, we need to add a 4 times 2, 8 atoms of hydrogen, 8 atoms of hydrogen. Okay? All of the elements need to be balanced. Okay, so let's look at the second reaction, second example here. So we have sodium chloride reacting with sulfur trioxide and water, producing sodium sulfate and hydrochloric acid. So let's look for an element that shows up in one of the reagents and in one of the products. I like to start here with sodium. Only here and here. There is 1 atom of sodium before and 2 after. 2 sodiums after. So let's introduce a 2 here. 2 times 1, 2 atoms of sodium before. 2 times 1, 2 atoms of sodium after. So this is balanced. Let's check the amount of sulfur before and after. Sulfur after, 1 atom of sulfur. And before, we have already 1 atom of sulfur. So that looks balanced. Now let's take a look at atoms of oxygen. Oxygen, we have 4 atoms after. And let's look at all the reactions and see where we can find oxygen. So we have here 3 oxygens and 1 oxygen. Therefore, 4 atoms of oxygen as well. So that's balanced. We can add a 1 here. And the only thing left to balance, or the 2 things left to balance, are the chlorine and hydrogen. Here is the only spot that we can balance hydrogen. 2 atoms of hydrogen before, just 1 after. Let's multiply by 2. Therefore, 2 hydrogens after. That's balanced. And let's just double check chlorine. 2 atoms of chlorine before. 2 atoms of chlorine after. So that is balanced as well. So check all the elements. If there is something unbalanced, you have to go back and try other numbers.
Is this part of the in-class assignment or is it just the first one?
What?
Is this part of the in-class assignment?
That's a new topic.
Okay.
course, it will show up in the next one. Okay, so C and D we will not cover here because of time constraints. Little more complex reactions, but it can be done. All right. Okay. Let's talk about our favorite reaction. So combustion reactions, they are special kinds of reactions, and they are very consistent regarding the products that are formed in this reaction. So complete combustion is defined as the burn of a compound in the presence of oxygen gas, O2. Complete combustion will always produce water and carbon dioxide. Always. If it is a complete combustion, it has to produce CO2 and water. And the physical state of some of the components are consistent as well, most of the times. Oxygen will always be a gas. CO2 will always be a gas. And water, most of the times, is formed in the liquid state. Okay, so when you write a combustion reaction, you have whatever you want to burn reacting with oxygen. That's going to oxidize the system, producing CO2 and water. Okay? So this is going to happen all the time. Most of the times you need to balance the reaction. So there is a trick here. Start looking at carbon. One carbon before, one after. So that's balanced. So add 1 and 1 here. Now look at the hydrogens, 4 before, 2 after. You need the number 2 here. And the last one to be balanced is always going to be oxygen. 2 atoms of oxygen from CO2, 2 atoms of oxygen from water. So that's a total of 4. Therefore, you need a 2 here to make it 4 after. Okay. So we start with carbon, look next at hydrogen, and then oxygen is going to be the last one to be balanced. This way, you can balance any combustion reaction. Okay, so let's take a look at octane. Octane is the main component of gasoline. So let's write the complete combustion for octane and balance the reaction. All right, first step, write the complete combustion reaction. Octane is going to react with oxygen gas. This is going to form carbon dioxide gas. And usually water in the liquid state. The reaction will come out always unbalanced, so it's our job to balance it. So I'd like to start looking at carbon first. 8 carbons before, we need 8 carbons after, and here is the only spot to balance carbon. Now let's move on to hydrogen. 18 atoms of hydrogen before. The only spot to balance hydrogen is right here in the water. And the very last element to be balanced is always oxygen. Let's take a look at what we have here. 8 times 2, that's 16 oxygens in the CO2. 9 times 1, that's 9 oxygens in the water. Therefore, we have here a total of 25 oxygens after the reaction. And the only spot to balance oxygen is in the oxygen molecule. Okay? So 25 before, 25 after, 2 before. So we will do a trick here. To go from 2 to 25, you simply multiply by 25 over 2. Or, if you want, you can multiply this whole reaction by 2 and end up with 2, 25, 16, and 18. Okay? Doesn't matter, they mean the same thing. I prefer to use the fraction because that will give the number 1 here and it's going to be easier. But it doesn't matter. Just pay attention on what we're doing. Okay, so the number of oxygens is always going to be the total after divided by 2. Okay? And that's going to be the coefficient that's going to come out over there. All right, so let's talk a little bit about side effects of combustion reactions. We will return to this topic when we talk about thermochemistry. Okay, so in a combustion reaction, if it is complete, you are going to generate a lot of CO2. CO2 is a gas that's going to be around here, forming here like a shell, and CO2 traps heat. So therefore, more combustion you have, more CO2 is produced, more heat is going to get trapped on Earth, and that will increase global average temperature. So that's one of the side effects of complete combustion. However, most of the engines are not maintained properly, and that creates another problem. Incomplete combustion will produce carbon, which is black. Okay? And in addition to that, carbon monoxide that strongly bonds to hemoglobin and doesn't allow oxygen to be transported. And if you have a high concentration of carbon monoxide, it will bond to all your hemoglobins and oxygen cannot be transported, and that will result in death. An interesting thing when you kill someone by high concentration of carbon monoxide, the autopsy will indicate heart attack and not that you were poisoned by carbon monoxide.
That's because your hemoglobin can't bond your oxygen.
Exactly. So the heart has to
overwork itself.
Exactly.
So you're basically giving yourself a heart attack.
Yes. Okay, so as you can see here, combustion has lots of side effects, but it is what it is, right? We need to use it and we use it. Doesn't mean there are no solutions, but it's an efficient way to produce energy. Okay, so I think this is a good point for us to finish for today. We have a good